So the week 6 videos were on image transforms. So the first one, there were introduction on the image transforms, then about one-dimensional unitary transforms, then one-dimensional unitary transform to two-dimensional transforms, then about Kronecker product and how it can be used to find out easily a 2D transform. So these were the topics in week 6. The first topic was image transforms. So why transforms? So it can be used as an alternative interpretation. Even so we are using a time domain representation. So instead of that, if you are using a transform domain representation, it is an alternative interpretation, and the processing can be speed up using image transforms. Like the convolution in time domain is multiplication in frequency domain. So if you are using frequency domain representation, it can be used to increase the speed. Then comes noise filtering. So noise can be assumed in a particular frequency spectrum. So by using Fourier transform, we can use we can filter the noise. Then comes compression. For compression also transformation can be used. So after we transform to Fourier domain, there will be some coefficients in some areas, so that can be removed. So this type of method can be used in the case of compression. Then comes sparsity. So these all are discussed in image transforms introduction. Then comes the types of image transforms. So mainly there are data independent and data dependent transforms. So data independent includes DFT, discrete Fourier transform, DCT, DWT, wavelet transform, and discrete sine transform. Then data dependent transforms are KLT or PCA. So data dependent transforms are actually data independent transforms. They have basis. They have already basis. So when an input comes, we can just apply a transformation. So bases are unknown. Bases are known a priori. But in the case of data dependent, we are finding the basis from the input image. So for every input image, KLT basis will be different. So this is about the introduction. So question 1, which of the following transforms is optimal for that particular kind of data? For a particular type of data, which transformation is optimal? So DCT, KLT, DFT. So we can say that data dependent transforms are optimal because we apply KLT on the input image itself. So its basis depends on the input image. So KLT can be considered as an optimal transform. DCT and DFT are not optimal for that particular kind of data. So KLT is the optimal transform. So answer is B. And we are comparing the performance of other transforms by comparing it with KLT. Okay. Then comes unitary transforms. So unitary transforms are a set of are a class of transforms where the basis, if the basis vector is A, then we can say that if it is a unitary transform, we can say that A Hermitian is equal to identity transformation. So A Hermitian is A conjugate transpose. Okay. And we can say that unitary transforms are norm preserving. So V square is equal to A. V square can be derived to U square itself. So if V is equal to, if a transformation V is equal to A into a spatial transform, spatial domain. So V is in frequency domain and A is in spatial domain. Then we can say that if A is a unitary transform, then we can say that V is equal to A square. V square is equal to U square. So that means the norm of input and norm of the output will be the same. Okay. Then in one dimensional case we will write it like this, right? That is, in transformation domain V is equal to a matrix A into U. Okay, then every element in, so V will be a vector, right? A will be a matrix and U will be a vector, right? So every vector in V, that is, this is V0, V1, V2, etc. So every vector in V of k can be represented as a dot product of U and AK star. U is what? U is this vector, so that into AK star. AK star is the columns of A Hermitian. So we know what is A. So we will first find A Hermitian, that will be a matrix like this, and every column can be represented as A0 star, A1 star, etc. Okay. So every column, so if you want to find a V of 0, the first element, then we have to take U along with A0 star is the first column of A Hermitian. So we know capital A, we have to find out A Hermitian, then we have to take different columns as A0 star, A1 star, etc. Then after finding the dot product, we will get V0, V1 to Vn. Okay, so this is the case of one dimensional case. Okay, then but our aim is to find out two dimensional transform. So first question is, which of the following is true for a unitary transform? Which of the following is true for a unitary transform? So we know that A, the fundamental equation for unitary transform is A into A Hermitian equal to I. So what will be the relation between A and A Hermitian? Just do A inverse in the left hand side and right hand side. So A inverse A Hermitian, A inverse I. So we will get A Hermitian is equal to A inverse. So the answer is A. Okay. But our aim is to find out 2D transform using 1D transform. Okay. So since we have 2D images. So in one dimensional case, I have told that if you have U, input matrix U, and the transformation A, you will first find A Hermitian, and from that you will find A1, A0 star, A1 star, etc. Then you will find the dot product between U and AK star to get the single element VK, right? In the case of 2D also, the procedure is similar. You should have U, but U will be a matrix, right? U will be a image, so it will be a matrix. Then AK will also be a matrix. That you have to find out. Okay. AK will be, AKL will be product of AK and AL. So if you want to find out A01, you have to take A0 star and A1 transpose. Okay, A1 star, and just find the product to find out A01. Similarly, if you have to find out A11, you have to take A1 star and A1 star transpose. So by taking the product of each A0, A1, A2, etc., AK, you can find out AKL star, and using that you can find out the 2D image like this. Okay. So this can be derived in a simple formula like this: V is equal to AU A transpose. Okay, this this equation can also be used to find out the transformation, where A is the input transformation. So if it is a DFT, we can say that A is equal to 1 by root 2 111 minus 1. Question 3. 2D image transform for an image is V equal to AU A transpose, where A is the input image and V is a transformed image. So what is the expression for U in terms of A? So you have to find out V is equal to AU A transpose. Then you have to find out U, right? So just multiply with A inverse V here, U A transpose. Okay. Then just multiply with A inverse here. So A inverse AU A transpose. So it will become I. So U A transpose. Then just multiply here right hand side by A inverse inverse and transpose. So here also A inverse and transpose. Then you will get U here, A inverse V A inverse transpose. Okay, so this is a basic equation, and you know that A Hermitian equal to I. So A inverse equal to A Hermitian. So and A inverse transpose A Hermitian is what? A conjugate transpose. So A inverse transpose is A star. So after multiplying, after substituting A inverse is what? A Hermitian. V A inverse transpose is A star equal to U. So this is the answer, A Hermitian, V A star. Answer is B. Okay. Then question 4. 2D image transform for an image is equation is given, V is equal to AU A transpose. Find the 2D DFT transform of an image U without using Kronecker product. So Kronecker product topic will come later. So we have U with us 1 2 3 4. Assume that it is an image and 2D DFT transform we have to find out. So A is equal to 1 by root 2 111 minus 1, that we know. Okay, so A is for one dimensional transform. Then this thing we have to use for transformation of this image 1 2 3 4. So this question is already there in the lectures. Then okay, so the equation is VKL. So each value VKL can be represented as the product of U and AKL star. Okay, so AKL star is the product of AK star and AL star transpose. So we know A, right? So A Hermitian can be written as 1 by root 2 1 by root 2. In the case of DFT, A Hermitian and A are the same, right? Because what is A Hermitian? A conjugate. But in DFT 2D 2 dimensional n is equal, for n equal to 2, it is only real numbers. So that conjugate and transpose will be the same as A Hermitian. Then so this is A0 star, this is A1 star. So first find A00 star, which is equal to A0 star A0 transpose. So you will get what? 1 by 2 1 1 1 1. So it will become 1 by 2 1 by 2 1 by 2 1 by 2. Okay. Then A01 you have to find out A01 star A0 star A1 star transpose, which is equal to, you will get it as 1 by 2 minus 1 by 2 1 by 2 minus 1 by 2. Okay, then A1 0 star also you can find out, right? A1 star A0 star transpose, that is 1 by 2 1 by 2 minus 1 by 2 minus 1 by 2. A11 star is 1 by 2 minus 1 by 2 minus 1 by 2 1 by 2. So we have all the AKL star with you. Just find what is V. So every V you have to find out. You can find out V00. For V00 you have to take A00. So A00 is here. Just multiply this with U. Okay. U you have no 1 2 3 4. So U equal to 1 2 3 4. Just multiply. Find the Frobenius now. Just find the dot product between these two matrices. That's all. So you'll get as 5. Then V01. V01 you have this one. Just multiply that with U. So you'll get V01 as minus 1. Then V10 you have to take this one. This thing is minus 2. V11 is 0. So you'll get V as 5 minus 1 minus 2 0. So this is your output transformation matrix V. Okay. So this is about without using Kronecker product, these are the steps. Like you have to find out A00 star, A01 star, A10 star, A11 star, and find the dot product between that matrix, and you will give V. Okay. Next question is the unitary 1D discrete sine transform equation is given, and you have to find out the DST matrix for n equal to 3. So the dimension is given as n equal to 3. So you have to find out what is the DST matrix. Okay. So it is a lengthy problem. So I'll just give a brief steps. That's all. Okay. So you have this equation Vk is equal to root 2 by n by 2 something. Then capital N is given as 3, right? So we can just write it as Vk is equal to n plus 1 means 3 plus 1 4. So 2 by 2. So 1 by root 2 sigma. So we can expand this sigma also. Okay. What should we write? U0 n equal to 0 means U0 sine pi k plus 1 by 4. I am using n equal to 3 here, right? So then U of 1 sine pi by 2 k plus 1 plus U of 2 sine 3 pi by 4 into k plus 1. Okay, these three terms only, because n equal to 0 to 2. Okay. Then find V of 0. Okay, V of 0, just substitute k here. So you'll get 1 by 2 U of 0 sine pi by 4, U of 1 sine pi by 2, U of 2 sine 3 pi by 4. So first we substitute n here and expand the summation, then substitute k. So you know V0, V1 is wait 1 by root 2 here. Okay. So here 1 by root 2 1 by root 2 plus U of 1 minus sorry, plus 1 by root 2 u of 2. Similarly, v of 2 we will get it as, so I will write in the next page, v of 1 becomes 1 by root 2. Okay, v of 0 is 1 by root 2 u of 0, u of 1 plus 1 by root 2 u of 2. v of 1 is 1 by root 2 u of 0 plus 0 into u of 1 minus u of 2. v of 2 is equal to so these are only substitution only, simple, but it may take some time, that's all. So you can represent v0, v1, v2 as in terms of u0, u1 and u2, right? Then you can write v as a matrix A into u, right? Then what would be A? These coefficients. Here 1 by root 2. So I'll write A as 1 by root 2 into 1 by root 2 is what? 1 by 2. Wait. 1 by 2, 1 by 2, 1 by 2, 1 by root 2, here 1 by root 2, 0 minus 1 by root 2, then here, sorry, here is plus 1, 1 by 2 minus 1 by root 2, 1 by 2. So this is the 2D DST matrix. So one dimensional 2D DST matrix is written like this, okay. So from this you can find 2D DST matrix using Kronecker product, that will be discussed later. So what is Kronecker product? So if we have two matrices A and B, like 1 2 3 4 5 6 7 8, you can find the Kronecker product between A and B as what? 1 into this thing, so 5 6 7 8, then 2 into this thing, so 10 12 14 16, then 3 into this thing becomes 15 18 21 24, then 4 into this thing 20 24 28 and 32. So this is how Kronecker product will be found out. So you have to first take one element from the matrix A, then multiply that value with every value in the matrix B, then write here and take other values and write it like this. So this is a simple one, no? So Kronecker product, by finding Kronecker product, the above transformation, not the 1D DST question that we did for finding 2D transformation of an image 1 2 3 4, right? That thing can be written very easily. Like we have used the equation V is equal to A U A transpose, and then we found A Hermitian. From that we found AK star. Then from that we find capital AKL star by using small AK star into AL star transpose. But without using all these equations, we can find this A, which is a Kronecker product between A and A. So the same A will be used as for finding Kronecker product. So we will find a 4 by 4 matrix, then just find the column representation of the image. So if the image is 1 2 3 4 like this, just write it as 1 2 3 4, then use Kronecker product matrix A. So this is U dash, okay. Then find V dash, say column matrix which will be equal to A into U dash. So you will get a column matrix like this. Just arrange this V dash as a V. V is equal to that is a square matrix. So it is much easier than the previous equations that we use for finding 2D transform. So we can use that connected product in this question. So question is 2D image transform of an image U is AU A transpose. Find the 2D DFT transform of an image U using connected product. So you have to find a 2D DFT. So first take the 1D DFT transformation matrix A that you know is 1 by 1 1 1 minus 1 into 1 by root. So U is 1 2 3 4. Okay, just find the column representation of that U. So U dash becomes what? 1 2 3 4. Okay, then without finding AKL star or something, just find the Kronecker product of A. What is that? A Kronecker A. Okay. So A Kronecker A, I have explained what. So 1 by root 2 and 1 by root 2 becomes 1 by 2, and this element multiplied with all the next matrix. Next matrix is the same, right? So 1 1 1 minus 1. Then the next value should be multiplied with all the elements. So 1 1 1 minus 1. Then this, the next one, 1 1 1 minus 1. Then comes minus 1. So minus 1 minus 1 minus 1 1. So this is our Kronecker product using the 2D DFT matrix A. Okay. Then the procedure is very simple. Like you can find out V dash as A into U dash. What is A? A you have to find out. 1 1 1 1 1 minus 1 1 minus 1 1 1 minus 1 minus 1 1 minus 1 minus 1 1. Then the column matrix corresponding to U 1 2 3 4. So just multiplication, you will get it as 5 minus 1 minus 2 0. So this thing you can convert that to B matrix as 5 minus 1 minus 2 0. This is the answer. So it is very simple, no? So just find the Kronecker product of that transformation matrix that you have to find out. So here the question is to find a 2D DFT transform. So just use A 1 by root 2 1 1 1 minus 1. So for the higher order matrices also. So if we have to find out A for n equal to 4, just write the matrix A DFT matrix for n equal to 4. That is a 4 by 4 matrix. Then just find the Kronecker product. Just multiply that with the column representation of U dash. That will give a product B dash in column representation. Okay, that's all. So this is Kronecker. This is all about Kronecker product. So the next one is assignment 6, shape from focus. So this thing is the assignment of this week, assignment 6. So for assignment 6, you have to know the topic of shape from focus that was discussed last week. So we have a number of images, like the image stack is here. From that we have we know every sharpness measure of every pixel at every image stack, Then from the sharpness measure you can find out the depth information. So that is what is in shape from focus. So so from the image stack you have to find out, you have to take a single pixel like this. So at every position you have to find out the focus measure. So for using that focus measure, so you will find out a plane with the maximum focus measure FM. Then you will find the, so and this position also you will find out, DM also you will find out position of that, say it is a fourth plane, so DM will be 4. Okay, then you will find out the third and fifth FM value. So that is FM minus 1 and FM plus 1. using that fm minus 1, fm plus 1, fm dm, dm minus 1, dm plus 1, and delta d. Delta d is the distance that we are shifting at every time step. So using that, you know the equation. So d bar is ln fm minus ln fm minus 1. Okay, so this is the equation. So you have to find out what for a particular pixel. Say pixel is 0 0. For a particular pixel 0 0, you have to find out focus measure on every pixel and find the plane at which there is maximum focus measure. So that is focus measure is fm and the plane index is dm. Then the previous frame find fm minus 1, the next frame find fm plus 1. Using these values and delta d, find d bar. So this is your A. Okay, d bar is the depth. Okay, so I have explained lab assignment here. So you have a stack of 100 frames like this. So frame 1, frame 2, etc. 100 frames are there. So at every frame, the sharpness of every point will be different. So here you can say that at some positions the sharpness is more, but in the second image sharpness is different than not in the second frame, 20th frame the sharpness is different from the first frame, right? And in the 40th frame the sharpness is different. So for a particular pixel you have to find out the sharpness measure for every frame, and you have to find out the frame at which maximum sharpness measure is there. So in the assignment there are only two functions, SFF and SML functions. So SFF function reads the image stack, so 100 images it will read, and neighborhood size also. So neighborhood size is for smoothening the depth map. So it is not required, but in the code it is required. So if you are using a smoothness measure, it will account the neighboring focus measure also. So it will help to smooth the that depth map. So you have to use the window size as specified in the question 1012. Okay. Then SML function takes the images and the neighborhood size and find the second order partial derivatives and the final SML. Okay. So what is SML? Sum modified Laplacian. So modified Laplacian is what? Mod fxx plus mod fyy. Okay. So first you have to find out fxx, then you have to find out fyy. Just find their magnitudes and add them to find modified SML. Then sum modified means you have to sum it over the neighborhood. Then you will get some value for every pixel at every frame. So this is what you have to do. So the steps are: read the image stack. Okay, read the image stack and call SFF function, to which pass neighborhood size q for SML. So inside this SFF function, call SML function to return SML of each of the images. So in SML function, for each of the frame, for each of the pixel, you have to find out the sum modified Laplacian value. So in SML function, what you have to do? fxx and fyy you have to find out. fxx and fyy, as explained in the last slides or in week 5 videos, you have kernels, a 3 by 3 kernel you have for fxx and fyy. Using that kernel, using already inbuilt function convolved 2D function, you can find out fxx and fyy and find their magnitude and find the sum to get the sum modified Laplacian and sum it over the neighborhood to get the sum modified Laplacian, and using that values find the SML value. Then SML value should be returned to SFF function. Okay. So in SFF function, from SML values for the entire stack, find dm with maximum SML value and the corresponding fm. Fm is the focus measure. Then find fm plus 1 and fm minus 1 from the neighboring planes. Okay, so using the above values, find the depth map. So this is the lab assignment. So you'll get a very interesting output as the depth map. It will be a dome shaped structure like this. In 3D, you'll get a depth like this. So this is about lab assignment 6. So each of the transformations will be explained in the next lectures in lab 7. So this is this lab 6, not lab 6, week 6 videos are about the introduction of transforms. That's all. So image transforms, 1D transforms, where we have to cover these transforms: DFT, DCT, DWT, DST, KLT, PCA. Then KLT is the optimum transform. Then unitary transform. So the transforms that we are dealing with are unitary transforms. A Hermitian is equal to I. Then one dimensional to two dimensional. So how we can find out the one dimensional transform? By finding a Hermitian and a K star. Then one dimensional 2D, we can straight away use this equation that we did here. Okay, and how you can find out BST matrix, I will also explain. Then about Kronecker product. So by finding Kronecker product, transformation can be found out very easily. Just find the Kronecker product between two matrices and just find the matrix product. That's all. Then about matrix assignments. So that's all about this week 6. So anyone has any doubts? Okay, that's all about today's session. Thank you.